Yeah, what was the first thing that we studied?
Yes, sir.
What was the first thing that we studied in the first chapter?
Sir, in the first chapter.
What did we study? So with you, Arslan, we have done this chapter recently, right?
Yeah, electric charges and fields, sir.
Yeah, so what was the first thing that we talked about? In electric charges and fields.
Sir, what are electricity and what is electric charges and stuff?
Electricity. So electricity is the third chapter, Arslan.
Electric charges and that's like so whatever is charge and all that stuff.
So we
Sorry,
talked
sir,
about the properties of
I can't
charge, right? So first,
remember. Yes, sir. Uh,
superposition principle. Yes, those superposition principle was there. Yes, absolutely. The definition of charge, right? And what was the definition of charge? So the charge was a peculiar property. We named that property. What was the name that we coined? Not we coined, but scientist or physicist coined. What was the peculiar property? What was it called?
physical property. So what's the question, sir?
So it was the intrinsic property. It was the
Yes.
intrinsic property, right? Charge was the intrinsic property of the material by virtue of which we experience electric force, electrical energy, and all those things. So that was the definition of charge, right? And then we that a particle or a material can have. So what was the smallest charge? Smallest charge was equivalent to 1 e, and this was 1.6 into 10 to the power minus 19. So this thing we studied. And then we studied about basic properties. And we talked about that all the atoms, they are neutral, right? Which means that the number of electrons and number of protons in totality, they are same. So they cancel each other out. So we have a neutral atom. And then we talked about basic properties of the charge. So there were four basic properties of the charge, right? What was the first property? What was
Sir, it can either be positive or negative.
can either be positive and negative? Yes, that is there. That is the features of the charge, right? So some there are yeah different polarity, but there were other basic properties,
Yes,
right?
sir. Think so. I think so. Think so. What you mean is like charge can be conserved and all that can either be created or destroyed.
Yeah, yeah. Oh, so that is conservation. Yeah, yeah. Conservation of charge is there, right? So in a reaction, whenever charges are participating in a reaction, or whenever a material is participating in a reaction, so the total charge in the left hand side, reactant side, should be equal to the total charge in the right hand side, which is the product side, right?
Oh,
So
sir,
when
you mean like conservation of charges and then like additivity and all that stuff,
yeah,
right?
yeah. So these were the basic, yes.
Yes, sir. Okay. Conservation, additivity, and uh, quantization. I think so. There was also.
So addition of charge is yes. Good. And then third was yes, as you said, it was that thing.
Quantization.
Vibration. Yes, absolutely correct. Now there is one left, quantization of charge. This was the most important of them all. And we got this formula, right? Where what is quantization? Oh, yeah, good. So what is the quantization of charge, right? So whenever you have a material, right? So this material would be made up of different elements or different whatever compounds and whatever so whatever the constituent contain, right? And we know that the smallest charge on a material is electrons. And in a chemical reaction, the ions or the compounds or the elements acquire positive or negative charges by the transfer of electrons. So only the electrons are making the positive or negative charges, number of electrons, right? So the charge on a material is dependent upon the electrons. How much free electron or how much electrons have been removed, how much electrons have been added to the material, right? So the charge on a material is quantized. Quanta meaning one small thing, right? One small entity, and that is charge on one electron. So one quanta, in this case, one quanta is E. Right, so this is one quanta, smallest unit. And on this smallest unit, you can combine these smallest unit and then make up a total charge, right? So your total charge on a material would be, let's say, some material has three extra electrons, right? E charge. Let's say some material has been removed by, let's say, 14 electrons. So then the charge on that would be 14 plus 3, right? So the total charge would be just these integers because electrons are integral quantity, right? There could be one electron, two electron, three electron, n electron, five electron, whatever. So the electrons would be in integer numbers, right? If you're adding, then you have negative charges. If you are removing the electrons, then you have positive charges, right? So depending upon the number of charges you have removed or number of electrons you have added, so the total charge on material would be the integral multiple of this quanta. This is quanta and this is integer, right? Integer number. So let's say if I say that charge on a material, right, is 3.5 E. So is it possible? Is it possible? Can a charge, can the number of electrons in a material would be 3.5, half electron? Is there a thing which is half electrons, right? So is it
No, sir,
possible?
not possible.
Yeah. So that is why we are telling it as integral multiple of a small quanta which is charge on one electron. So that is what do we mean by quantization charge, right? That charge on a material is always some number of electrons, right? So that is how we define that charge, quantization of charge. So this is not possible. Okay, clear? Am I?
Yes, sir.
Yeah. And okay, so this thing we have used numerous times, right? So if we were calculating the number of total number of electrons in a conductor, right, in a conducting material, there we have used this, and we have used this thing so many times, right? So in magnetic materials, in current electricity. So in those things, these quantization of charge we have used numerous times. Okay, what is the next property that we understood in this thing? What was this is invariant of this was the four basic properties of the charge, the frame of reference, right? So it is independent. Whatever frame you choose. So let's say the charge of something is plus 3e. So if some other person which is moving with some velocity, charge is a scalar quantity. Yeah. So charge is a scalar quantity. That thing is, that thing is the features of the charge. So that is not the basic property. So that thing we can write in here. Charge is a scalar quantity. But the four main properties, so these were the features of the charges, right? And the four main properties were the conservation, addition, quantization, infinity. So these were the four important properties of the charge, right? Yeah, obviously charge is a scalar quantity, right? So, okay, so after understanding the properties of the charges, so what are the other effects of the charges, right? So how does it affect the surroundings? Right? The one the Coulomb's law, or this is also called Coulomb's force. And this was a very important quantity that it said that if we have two charges, right, let's say Q1 and Q2, and the separation between these charges is, let's say, R, right? So the force between these charges would be directly proportional to product of these charges, and it would be inversely proportional to the square of the separation. And if we remove this proportionality, so we'll get a constant k, and this was and this k 9 into 10 to the power 9 Newton meters per this was the value of this k, and this k is the 1 by 4 pi epsilon
The voice is
permittivity of free, right? So
So your voice is cracking.
which means that the force, Coulomb force between two charges, my voice is cracking.
yeah.
Yeah, is it crack for you?
Sir,
Yeah, also I got internet, yes. Internet. Okay, so now the ping is 81 ms. How is it now? Is it still cracking, guys?
No, sir.
Is it still cracking?
No, sir.
No, sir.
Oh, yeah, yeah. Yeah. So what are we talking about? Yeah. So this, so we can write the Coulomb force, right? This Coulomb force is 1 by 4 pi epsilon naught Q1 Q2 by R square, right? And remember, force is a scalar quantity or a vector quantity. What is force? Yes, force is what?
Scalar.
Scalar quantity. Force is a scalar. So you know that to represent the force, we have to also represent the direction, right? Force, electric field, all these things, right? So these are, let's say, torque and dipole moment. All these things are a vector quantity, right? And then you have work done, and then you have potential, and then you have, let's say, energy. So I should write U. So these are scalar quantities, right? So these things are scalar, these things are vector. So force is a vector quantity, right? And we need direction to represent that. So how do we get the direction? So direction is dependent upon, let's say, the polarity of the charge, right? So equal charge will repel each other. Equal charge will repel each other. So force would be repulsive and alternate charges. It's still cracking. Right hand thumb rule. So in here we don't have any right hand thumb rule, right? In here we don't have any right hand thumb. Right hand thumb rule we use in current, right? In here we don't have any right hand thumb. Whenever we have cross product or something like that, so from there uh, we determine the force, the direction of it, right? In here we don't have any right hand thumb rule, but yeah, how can we apply, right? So alternate charges attract each other. So let me show you one example, and then it will be easier to understand. Okay, but before we understand about the direction of force, let us also understand about the medium, right? So let's say that if we put so influence or effect of medium in Coulomb force, right? So let's say these two charges, these two charges were in the air, right? There were no any medium between them. But if we put this thing, if we put these two charges in a medium, then what will happen? So then the force will change because we know that Because we know that the force is dependent upon this medium, right? So this force is dependent upon the. So then what would be the force? So let's say this is the separation. These are the two charges, right? And if we have placed this thing in a medium, let's say we have put these two charges in water, right? So if we put these two charges in water, then the force will be effective, right? Then the force will be increased or decreased. What can you guys tell me? If we put these two charges in the water, then what will happen to the force? Will it increase or decrease?
Sir, it will decrease.
Decrease. Okay, so how can you say that? What is the reason behind that? Both of
Sir,
you guys, yes,
because
yes. Okay, so let us see that, right? So we know that force will become how much? So force will become 1 by 4 pi and not epsilon naught but E, right? And then Q1 Q2 by R square. And we represent one quantity which is called dielectric constant, which is called dielectric constant or relative permittivity. And what is that? This is represented by K, right, or ER, and this is the ratio of permittivity in medium and ratio and permittivity in free space, right? So this is how we represent this dielectric constant. So K is E by epsilon naught. So this E would be how much? This would be epsilon naught and K, right? Where E is permittivity of a medium and then epsilon naught is permittivity of space and K is the dielectric constant. Right. And this K is always greater than equal to 0. Right. So this K is always greater than 0. Right. So then what will happen to the force? So your force is in place of this epsilon. What we can write? We can write 4 pi epsilon naught K, and this would be Q1, Q2, and this is greater than 1 part. So this is Q1, Q2 by R square, right? And we know that, let's say this is medium, right? This is medium. And you guys can tell me, right? You guys can tell me that how much is this thing? Because you see that 4 pi epsilon naught Q1, Q2 by R square. If we can take out these things, right? This thing, and what is remaining? 1 by K. So what is this thing? Can you guys tell me what is this thing?
Coulomb's force.
Yeah, so that is in the air. Force in air. right? And multiplied by 1 by k, so that is k, right? So you see that this thing is always greater than 1. So this F medium would be smaller than F major, right? This is how we say that the force in the medium will decrease in the medium. So that is how we write it. And the dielectric constant for water, this is 80, right? This is 80. And for air, we obviously know that for air that would be 1, right? So these are the things that we learn from Coulomb force and the dielectric, right? So did you guys understand that why this would be decreased? Why this would be decreased?
Yeah.
Yeah. So this is how we say that this would be smaller than F medium would be smaller than, let's say, equal to F medium. So these are the things, right? You guys please note down this part. And then we will talk about the superposition principle that Mariam was saying. And then we'll talk about electric field lines, and superposition of electric field and all those things. So please note down, guys. Please quickly note it down. And you guys also start your revision, right? I am doing these parts, and if let's say I can also pick some questions, and yeah, the revision part I will skip. Some of the derivation, if you guys want to, yeah. So if you guys have some confusion in those derivation, and if you guys want to talk about that, so you guys can tell me. Otherwise, we will skip, and yeah, we'll quickly try to finish this. Got disconnected. Yeah, so please note it down. That's it down. And whenever you want to scroll, you want me to scroll the screen, please. Yes, one moment, guys. Yeah, whenever you guys want me to scroll down the screen, please.
Yes, sir, you
And
can just scroll down a bit, sir.
yeah, and what I will do is that I will send you a PDF which will contain all the derivations that you have to study. Right, I will send that PDF, and let me check that.
Sir, can you please scroll down?
So I have shared with you guys some important questions, right? And you guys can look at those questions. Yeah, I have already sent this. You guys can look at that in the video. So in every chapter there are very few important questions, and you guys can look at those questions. Let me forward this. Yeah, whenever you guys want me to scroll this, uh, and then there is derivation part also. It is that. Yeah, whenever you guys go, I had my physics. Oh, you had physics. How did it go, Maria? How did it go?
It was good.
It was good, good, good. Yeah. And now you have learned that which portion you have to cover, right? What are the portions that you have to cover, and in which part you don't have any problem? You can send me that question paper.
Prob
Yes.
Yes, sir, I will send.
Yeah, please send
I
that
have
question.
uh, as far as yes, sir. As far as I saw the paper, I was having difficulty in AC most.
AC. Okay. So
Yes,
in
there were
AC,
there were
in
many numericals of AC.
yeah, yes, numericals are there, right? So we can talk about. So please send that question paper in the group, and then in the next class, yeah, we can also talk about those questions. So simultaneously, we can talk about those questions. And okay. So in AC, in the LCR circuit, okay, so that will be the check. So please send that question paper in the group, and then we can. So yes, guys, please
Okay,
note it
sir.
down.
Yes, sir, I'm done.
Yeah. Okay. So then this part also noted.
1 second. Yes, sir. Tim.
Okay, so the next thing that we studied, what was that thing? The direction, right? So we can write the force in vector form as k q1 q2 r r hat and r square. So this thing we can write. Or we can also write this as kq1 q2 r vector divided by r cube. So these are the vector form. And if we write the positions, right, if we write the position vector, then how can we write this thing? So let's say you have, right, so let's say you have this x and y coordinates, right? And let's say you, right, so let's say the position vector of one charge is r1, and this is position vector. And then you have another charge which is, let's say here, right? This is q2, and this position is what, r2. So these are the position vector of these two vectors. And then I want to calculate the force between, so force on charge 1 due to the second charge, right? This would be how much? So I am calculating the force on this charge due to this charge, right? So let's say this is the distance between them. So what do we know about this separation? How much would be this separation? Let's say if I write it like this. So we already know the vectorial sum, right? We already know the vectorial sum. So what is the vectorial sum that we will use to write these? Let's say this vector is x, right? Or let's say this is r1. So how can we write this r12 vector? What would be this r12 vector? Yeah. So if you guys, yes, we will use the triangle law, right? Triangle's law of vector addition. And I have skipped the vectorial part, right? Because you guys already know the vector. Pythagoras, the parallelogram law, the triangles law, vector addition, and then dot
Yes,
product,
sir.
cross product. All these things we have discussed so many times, right? Orthogonal vectors, the universal unit vectors, I, J, K form, all these things we have discussed so many times, right? So I will just directly use. So let's say if this is A vector, this is B vector, then what is this vector? What is this vector from triangle's law?
A plus B.
A plus B, right? So this is the resultant vector A plus B, right? So we have to put the head of one vector onto the tail of the other vector, and then we connect the tail of one vector to the head of the other vector. So that will be the resultant vector, and that would be A plus B. So similarly, we have this vector. Let's say this is A, B, and C. So AB plus BC would be in vectorial addition, not the triangle, the magnitude part, not the magnitude part. So AB vector or the position vector R1 plus R2, that would be how much? R2, right?
BC.
So if we calculate, yeah, so if we calculate this BC is R12, right? AB is AB vector is R1 plus BC vector, that would be your AC vector. right? Not CA. CA is different. I'm writing AC. So this is the vector. So R12 would be how much? This would be R2 minus R, right? So if I calculate this separation, BC. So BC is how much? This is R1, right? So if I want to calculate the force on one charge Q1 due to this two, so that would be simply K Q1 Q2 and magnitude BC. This is the separation square. And what about the direction? What would be the direction? Direction? Can you guys tell me? Yes. What would be the direction? Yeah. What would be the direction? Let's say that would be BC hat or CB hat. I'm calculating the force on this charge due to this charge. So what would be the direction? Will it be in this way? This is quite important and we discussed this thing so many times. Will it be this way or will it be this way? What would be the direction? Yes. So this direction is BC hat. This direction is CB hat. What would be the direction? On this point, due to this Q2, what would be the direction, guys?
BC hat.
BC hat. So Mariam is saying
BC hat.
BC hat. Mariam is saying BC hat. What is your answer? Uh, what is your answer, Arslan sir? What is your answer? So you guys have yes, tell me. I want you guys to clearly understand what is happening, right? If you guys have any little bit of any doubt, yeah, trivial doubt, please tell me. Yes, what is your answer? What do you think, Arsalan? What would be the direction, BC hat or CB hat? If I change the name, right, then you guys will quickly tell me. So, but first I want you guys to uh, think and come up with an answer. Yes, boss, Arsalan,
Yes, sir.
what would be direction, BC hat or CB hat? And remember, the test charge is always what, positive or negative? These Q1, Q2 are positive, unless and until it is mentioned. So they are always positive. So what would be the force on BC, right? Yes, Ursula. Any answer? There are two options. Binary, BC hat, CB hat.
Uh, BC hat.
Okay. So hat, same answer, Ursula. Okay, किया जाए two answers, right? Okay. So if now I will change the name. So force on this force at B due to C, right? And this is positive, this is positive. So force would be attractive or repulsive. Now you guys tell, what would be the force? Attractive or repulsive?
Repulsive.
The repulsive is what direction? BC or CB?
CB.
Right? Yes, Arsalan sir. Clear. Yes, is it clear? Yes, Arsalan, where are you? Is it clear?
Yes, sir.
Yeah, so the direction would be a CB hat, right? And I have written in 1-2 notation. So in 1-2 notation, this is what? In 1-2 notation, this is Q1, Q2, R2, 1 hat. And this is BC, which is R. I can write it because magnitude of BC vector that is same as CB vector. So in magnitude part, I can write whatever I want. So I can write it as 1, 2, right? And this square. And you guys can see that R21 would be how much? This would be R1 minus R2, right? So I can write this thing as I can write F12 hat as KQ1, Q2, and this was R21. So this is R1 minus R2 magnitude divided by R1 minus R2. This is the like, not the magnitude, but this hat is the R21 hat and magnitude square. So if I write it in vector form, so this would be how much? This is Q1, Q2, R1 minus R2, and this would be R1 minus R2 and whole cube. So if I write it in vector form, so this would be Q. This is the answer. This is in vector form, right? So if we are given two coordinates, right? If we are given two coordinates, then how do we calculate the so let's say if we will do one question, then it will be clear. So charge Q is placed at let's say 305 and another charge, let's say Q again is placed at 2, 3, right? Then what is the force between them, right? So this is how, so then we will use this formula, right? So what would be the position vector of, and we have to calculate what is, let's say, what is the force on charge, let's say this is Q1 and on Q1, Q, so what would be the force, right? And what are the things that we need to calculate? We have to calculate R1, R2, and then their magnitude, right? So how can we do that? Do we remember how do we write the position vector? What would be the position vector of Q1? What would be that? What would be that, Arsalan? What would be the position vector of Q1?
Sir,
Yes,
So the position vector of Q1.
How do we write the position vector? If the coordinates are given, how can we write the position?
So if the coordinates are given.
Yes.
Let me think a bit.
Yeah. So this would be 3i plus 0j plus 5k. This is how we write. So this would be 3i plus 5k. And similarly, if we write R2, so this would be 2i plus 3j plus 4k. So
Yes, sir.
this is how we write the position vector, right? And now we have to calculate F12. This we know that this is how much? Q1, Q2, R1 minus R2 divided by R1, R2 magnitude the whole cube. Right? This is vector and this would be how much? K, Q1, Q2, and they can also give you the numbers, the value of the charges they can give. Right. So this would be R1 is 3i plus 5k and minus of 2i plus 3j plus right, divided by this thing 3i plus 5k minus 2i plus 3j plus 4k and then its magnitude and q. So what would be this thing? So k q1 q2. This is 3i plus 5k minus 2i minus 3j minus 4 divided by this thing again. So this is 3i plus 5k minus 2i minus 3j minus 4k and magnitude q. So then what we will get? 3i minus 2i is I minus 3j hat and plus k hat divided by this thing is how much? I minus 3j plus k hat magnitude q. So what is the magnitude of this thing? Tell me what is the magnitude of this, let's say A vector. What is the magnitude of this thing? Arsalan, if you remember, what is the magnitude of this thing?
So magnitude would be
Let's see if you remember the vector part.
hmm, hmm,
So do you remember the universal unit vectors?
yes, sir.
These are a very, very crucial thing. And I have told you that you calculate the magnitude of this. How do you calculate magnitude? Okay, to remember this thing or AXI,
Oh, yes, sir. Yes, sir. You take A,
YJ,
B, I,
and
J, K, and then
AJK.
you make like
I'm talking about only the magnitude of what is the magnitude. This was AX square, AY square, and AZ. This was the magnitude, right? Right? Good or how much? That would be 1 square and minus 3 square and 1 square again. This would be of 1 plus 9 plus 1. So 11. So this would be how much? This thing would be k q1 q2. This is vector divided by root 11 power q. So this would be k q1 q2 I minus 3j plus k hat and 11 power 3 by 2. So this would be the answer. Is it clear to you? This vector part is very crucial. Is it clear?
Yes, sir.
Okay, so then please take down, right? Please down from here. Vector notation. Yeah, whenever you want me to scroll down, please tell me. So in here I can also add magnitude of this thing is equal to magnitude of this thing, right? Because this from here to here, the distance magnitude would be same if I go from here, if I go from here. Only the direction would be different. Right? This was a very crucial vector form. Whenever you want me to scroll down, please.
Yes, sir. Sorry, sir. You were saying something? It's very laggy
Yeah,
for me,
so
sir.
oh, so my voice is still cracking. Is it cracking
No,
or?
sir. I think so. It's my internet that's lagging. My grandma's also
Yeah,
talking like I'm getting
yeah, yeah.
distracted.
Yeah, yeah. So I was saying that this R12 magnitude, right? So this magnitude is same if we go from here to here. So if we go from B to C or if we go from C to B, then the distance traveled is same, but the directions would be different, right? So if I write direction, so direction would be different. R2 had, so R2 had, this direction would not be equal to this direction, but the magnitude part, this magnitude would be equal to this part. So that is what I was saying, right? Yeah, whenever you want me to scroll it down, please this is force on one due to this thing we have to always. Yeah, whenever you want me to scroll it down, please. Yes,
Yes,
whenever
I
you
do.
have done, then please look down. Right. So then you can easily understand that if you want to write F12, right? If you want to write F12, so that would be simply this thing. So remember this thing. Whatever you have written first, so that will come first. And this would be the second. This is how we write in vector form, right? Yeah, but whenever you have written this part, please
Yes, sir.
yeah, then please write it. There is a hat over here, right? Hat, and this is changed to vector.
Sir, your voice is very low, sir.
My voice is low. How is it now? How is it now? Is it okay?
It's somewhat.
Okay, so how is it now?
Yes,
How is it?
it's somewhat okay, sir. Just my grandmother is talking, so I can't even hear.
Oh, yeah. So, because I have increased the volume to the fullest. Yeah, okay. Whenever you want me to scroll down the screen, please.
Yes, sir. Scroll down, sir. I'm done.
Then please. So these are very important questions, right? Please, yeah, or prepare these questions very carefully, right? And if you have slightest bit of doubt, so please tell. Yeah, whenever you want me to scroll it down, please tell.
Yes, sir. Done.
Then please, and always, yeah, so please start practicing the questions, right? Yes.
Yes, sir. I'm done.
70. Yeah. Okay. So then let us understand another topic, which is force on a test charge. You right. So what is the force on a charge due to multiple charges? So let's say you have a test. Let's say you have a test charge here. This is a test charge Q, and then you have the source charges, right? So let's say you have Q1 charge here, you have Q2 charge, you have Q, let's say Q4 and Qn. So these are the charges, and the separation is, let's say this is R1, this is R2, and yeah, something. And then in the last you have Rn, right? And right, due to n charges. What would be that? This would be the superposition of all the individual charges. Right, so this is what we call the superposition principle, right? And the correct this part is that it says that the force would follow vector addition, not simple algebraic addition. The force due to multiple charge per so how much would be that? So this would be KQ Q1 divided by R1, let's say square, and R1 hat plus KQ divided by R2 square, and R2 hat plus KQ3 and R3 square, R3 hat, and so on. And you have KQQN, Rn hat divided by Rn square. If you can take KQ common, so this would be simply Q1 by R1 square, R1 hat plus Q2, R2 square, R2 hat plus so on, Qn by Rn square and Rn. So this would be the total right. So quickly note it down, and we will do some questions next class. But after 3 minutes, right, whatever class you missed yesterday, So we'll talk about that. Right, whatever we are doing in the background. At 8 o'clock, you have another different exam, right? Yeah, please note it down, and then we'll jump to magnetic field. Yes, whenever you have noted it down, please.
Yes, I'm done.
Done. Okay, this part also. Yes, noted.
Yes, sir. Yes, sir.
Yeah. So, like, what kind of question comes, right? So, let's say you have, yeah, we'll talk about that in the next class. But let's say if you have three charges on the vertices of equilateral triangle, right? These charges are on the vertices of equilateral triangle. So let's say this is L, this is L, this is L. And then you want one point, or let's say A, B, and C charges here. And you want to calculate force on B, right? So that would be how much? That would be force due to A and force due to C. So that would be right. And we can also write BA and so here we will use the superposition principle, right? We will calculate the force due to this thing and force due to this thing. So that would be right. Okay, so yeah, and there are other questions as well that if you have four charges at the corner of a square and then you want to calculate the force somewhere say at the center or whatever. So these kind of questions are there, right? And then you have to use the superposition principle. So that is why this is important. Okay, so now we will stop whatever back up. Like, I have missed so many classes, and right today I have been able to catch you because yeah, you were missing so many classes, but now today I have been able to catch you. Now we will start this. Right. Okay, so let's take a 2 minutes break and then yeah, you can have some water and whatever you want. Let's take 2 minute break and then right.
Sir, isn't the class
So
over?
in the meanwhile, you can yes.
Sir, sir, class is
So there
over.
is
It's
another
5:30. Huh?
yeah. So there is another class, right? The one class that you missed, the backup class. So at eight
So how
o'clock.
long will this be? I have another class also.
You have another class where?
Sir, a chemistry class, sir.
That is 1 hour later,
Yes,
right?
uh, yes, sir, it's at 8 p.m., so never mind.
So yours 8 p.m.
Yes, sir, for me, 8 p.m.
For you, if it is 8 p.m., so which means
Yes, 30, sir, 1.5 hours there.
1.5. Yeah, so then we can take this class of 1 hour, right?
Yes,
So 1 hour class
yes, sir.
because uh, because we missed so many classes, right? And you have to complete that. So please, you take out that notebook in which you were doing this fourth, right? So in the backup, please take out that notebook and let's take 2 minute break and then we start again. Okay. In the meantime, we can have some. Okay. So yeah, yeah. Did you bring that notebook in which you were noting down this thing?
No, sir.
So yeah. So we understood about this Biosavar's law, right? And we also understood about the application of that Biosavar's law, right? And yeah, we calculated the magnetic field due to different kinds of distributions for straight wires and for circular wires calculated. Now, there is another law which is used to calculate the magnetic field of continuous distributions, right? So that is Biot-Savart's law that we studied in the last class, and it says that this quantity, the closed line integral, this thing of magnetic field, this is simply mu naught I. This is right. And what is the application of this thing? So there are several applications, and two of them mainly are yeah, application of application of ampli- so there are mainly two applications. One is to calculate the magnetic field of thick wire, right? And another application is calculate the magnetic field of solenoid. Right. So these are the two main application of Ampere's law. Right. So let us understand that how do we calculate the magnetic field of thick wire using the Ampere's so magnetic, and this is very important. So magnetic field of thick wire. Right. So then let's say we have this thick cylindrical wire, right? And let's say that I current, right? I current is flowing through this thick wire. So the current which is flowing, that is I, right? And the radius of this thick wire is let's say. So how many regions are there for this thick wire? How many regions are there? How many regions are there?
Sir, three.
Yeah, what are the regions?
Sir, the two circular ones at the top.
So those are
So one.
surfaces, right? Surfaces. I'm not talking about the surfaces. Yeah, absolutely right. There are three surfaces: top one, bottom one, and the curved one. So this is
Yes,
a
sir.
solid wire, right? This is a solid thick wire, right? So let's say you have those poles, cylindrical poles. So that is the conductor, and the current is that. So I'm talking about that. So there are mainly two regions, right? One is inside, and the other one is outside. Let's say this, right? So then there would be two kinds of magnetic field. There would be thick wire, right? And one would be magnetic field inside, and then magnetic field outside, right? So now let us simply we can calculate the magnetic field outside very easily, right? That thing we can calculate. So let's say we have this. Let me calculate magnetic field outside. So we have this thick wire, right? And I want to calculate the magnetic field. Let's say at this. So what I will do is that I will make an Amperian loop, circular. This is a circular Amperian loop, right? And let's say this distance is how much? So this distance is r, and this is Amperian, right? And this is our disk like shape, right? So you have a cylindrical wire, right? And let's say you have this cylindrical wire, and then you take a disk outside of it, right? So some r distance disk around it. So that would be your Amperian. So we know that if we apply the Ampere's law, right? So applying the Ampere's law, what would be, what does it say? So P dot dl, that is how much? Mu naught and I inputs, right? So P, right, and this is P dot dl, right? So dl is how much? This dl is this thing. Let's say this is dl, right? This much distance is dl that we are talking about. And this is this magnetic field is perpendicular to that. So this is at 0 degree, right? This B and DL, those are at 0 degree. So the angle between them is 0 degree. So P dot DL would be simply, this would be simply P DL and cos of 0 degree. And this is mu naught I. So we can take out this b, and cos 0 is 1. So this is only the integral of dl. And this is mu naught. And how much would be within this disk? How much current is passing through this disk? How much current is passing through this?
Hmm. Sir, how much current is passing through the disk?
Yeah.
So current will be equal to around.
So this whole disk, this bigger disk is incorporating the whole current, right? The current which was passing, the whole current it will take. So the whole current is I. So that would be simply I,
So,
right? And what would be this DL integral, this total DL, what would be that? What would be that?
sir, it will be
This is DL. And what would be this total? The
DL
circumference of
pi r
the
square.
circle, right? That would be that.
Yes, sir.
2 pi r, 2 pi r, that is length, right? So that would be 2 pi r. And this is mu naught I. So what would be V? V would be simply mu naught I by 2 pi, right? So this, remember, this is the magnetic field outside, right? So this is the magnetic field outside. This is mu naught I by 2 pi r. I is constant, mu naught is constant, 2 pi is constant. So V outside, that is varying as 1 over r. Is it clear?
Yes, sir.
Is it clear?
Yes, sir.
Okay, so now let us calculate the current in. Yeah, so now let us calculate the current inside. So let's say again we have the same disk or this cylindrical wire, and we are calculating the the magnetic field at this, right? So then we will again make an Amperian loop, right? We will again make an Amperian loop like that, right? And this distance is how much? This distance is r. And the bigger distance is how much? This is r, right? Now this is the Amperian disk that we are taking, right? So from this one, how much current would be passing? Will it be same as the previous one? Will it be same?
How much current will be passing, sir? So yes, sir, it will be the same.
So there are these portion which are left, right?
Yes, sir.
So
But sir, if
these are
the area is less, doesn't mean that the current should be like less, right? Because it's still going to
Yeah, the
For
current,
the entire area.
yeah, I'm talking about the current enclosed, I enclosed in that area,
Oh, okay, sir.
right?
Then yes, sir, it will be different because it's
Yeah,
much more.
yeah. That is the idea of the Ampere's law, right? The Ampere's law says that I enclosed in the Amperian loop. Whatever loop we have taken, the current enclosed in that. So that would be, as you have said, that would be different, right? Earlier we were taking the whole thing. So in whole thing, this same current is passing, right? Which was I. Now, as you said, that this would be different. So what do we know? The current which is passing through this whole area, that was I, right? And let's say the current that will pass through this part is I dash, right? And from whole area that is I. So from pi r square passing this part is pi r square, right? Is pi r square, right?
Yes, sir.
So now we have to calculate the current through what region? So let's say this is 1 by, if I calculate in unit area, so that would be I by pi r square. And in what region I have to calculate? In what region I have to calculate the current? What is the region that I have to calculate the current? Yes,
Sir, only the region of the disk, sir.
this disk. So what is the disk area of the disk? This is pi r square, right?
Yes, sir.
So this would be the current, which would be passing through this area. So that would be how, that would be I by pi r square and into pi r square. So this part will cancel, and I dash, that would be how much? That would be I r square divided by r square. So this would be the current which would be passing through this amperian. So let me write it. Amperian. That is the items. Right. So now let us again applying the Ampere's law. What would be that? Again, this would be P dot dl and mu naught I in. So that would be how much? Again, dl is inside and the dl is again going inside. So that is again 0 degree. So P dl cos 0 degree, right? Dash. This is again D is taken outside dl and mu naught I dash. Can you tell me again what would be this dl integral? What would be that? What would be this dl integral? If I integrate this dl over whole closed loop, so what would be that? What is this line integral dl? What is this total length? Yes, again that is 2 pi r, right?
Yes, sir.
Circumference of the circle. Then this would be pi r. And this I dash is how much? That is I divided by. So if we calculate the magnetic field, that would be how much? Mu naught I r I r square divided by r square and 5. This r will cancel this thing, and this will be how much? So magnetic field would be mu naught I r divided by pi r square. So we can see that this is magnetic field inside. V inside is how much? This is mu naught I by pi r square and r. How is it varying? How is it varying? We see that mu naught I 2 pi r square, these are all constants. So V inside is directly proportional to R. And what was V outside that got? This was 1 over R, right? These were the two things that we got. So if we plot this thing, right? If we plot the magnetic field over this R distance, so what would be the graph? And this graph is very important, right? So they all, and let's say this is the radius of the cylinder, right? So this region is inside region, right? This region is inside region. This region is outside region, right? Because this region is less than R. This region is greater than R, right, Arslan?
Yes, sir.
Right?
Yes.
So this would be straight line, and then it is going inversely over R. So this would be this like. So this would be your behaviors. This is directly proportional, and this is inversely proportional. So this would be the variation of magnetic field of a thick wire. So inside it is directly proportional, outside it is inversely proportional. So yes, is this thing clear? Yes, Arsalan, can you hear me? Yes, can you hear me, Arsalan?
Yes, sir.
Yeah. So is it
Sorry, sir.
clear?
It's lagging a
Any
bit.
doubt? Is it? Yeah. So I can understand. Maybe one of us. So one of us have a bad, right? And I guess that's me. So yeah, please note it down, and or if you have any doubt, please tell.
Yes.
What? Please. This one is a very important. Well, yeah. Whenever you want me to scroll down, please. Yeah, whenever you want me to scroll down the screen.
Yes, sir. Done.
Yeah, then please. uh, down.
Yes, sir.
Done. Okay, then please note down.
Yes, sir. Done.
Yeah, whenever like done. Okay, then note down this stuff. This stuff is yeah. So whenever you have noted, yeah, so this behavior, this is very important. It will straight and then it will drop down.
Yes, sir. Yes, I'm done.
Not done. Good. So now let us understand another application, that is magnetic field of solid. Is again very important. This is the circular terms, right? And let's say this length is L, right? And there are n number of turns, number of total number of turns. So what would be the magnetic field due to this? So, so that we calculate using this ampere or this ampere's law. Let's say the current is passing like right. So current is going like this is going inside, right? Current is going inside, so magnetic field would be where? If the current is going inside, if we apply the the thumbs Maxwell thumbs rule, right? So then what would be the direction of magnetic field? That would be in this direction. Right? Is it clear to you?
Yes, sir.
So this is the direction of the magnetic field. Then how do we take the Amperian loop? So we make a rectangular Amperian. That is like we make an Amperian loop like this. And we are going from here, here. Let's say this is A, B, C, and D. This is the Amperian loop we are taking, right? Now you tell me that what would be the let's say what would be the current which is so let's say the total current which is passing through this thing is I. In one turn, the current is I. So this is how calculate. And then let's say you want to calculate the magnetic field in this loop. So applying the amperes so that would be how much? So this would be V dot dl, and let's say this is mu naught I in, right? And remember, let's say this length is whatever length, right? Let's say this length. So the total length is L, right? Total length is L, and this length is simply small l, right? So then what would be the magnetic field in this so we know that V dot dl closed integral. So there are four loops, right? So one would be the magnetic field due to AB length, right? So this would be V dot this AB length, right? Plus this V dot this is what length? BC length, and then V dot this length CD, and then you have V dot this length which is DA, right? So this would be the closed loop, right? From A to B, and then B to C, then C to D, and then D to A. So this is the closed loop. And then this is equal to mu naught. And how much is the current which is in, right? So that would be, let's say, n number of turns which is there into this I current, right? And how do we calculate this n? So this n we calculate using number density, right? What is the number density? So number density is I by n. So this or this is n by n, right? So number of turns per unit length, right? Let's say this is your n. So this n would be how much? This would be n and l. So the current which is passing through this region, that would be how much? That would be n, l, and I. That would be the total current, right? Because this is Ni and N is how much? That is Nl. The current which is passing through these dots, that is simply NLI. So this would be mu naught NLI, right? Is it clear to you why this would be NLI? Is it clear?
Yes, sir.
Yeah. So then, yeah. So then let us calculate all these magnetic. So what can you tell about the magnetic field in this AB line or AB length? This magnetic field is perpendicular to this magnetic field, right? This line is perpendicular to this magnetic field. So your B dot AB, that is cos 90, right? This is BAB and cos of 90, right? And this is how much? This is and this is not 80, right? Okay, and then what is the other thing? So B dot BC, right? Do you have any magnetic field in this region? So this is outside this solenoid and this BC region. So magnetic field is zero outside this region. So in here, this is zero. And then again, this is B and CD and cos 90. And then this is how much? So this is B and this length L, this is BL cos and this is mu naught NL. So this part is zero, this part is zero, this part is zero. So we only have BL cos 0 is 1. And this is mu naught NLI. So this L and this L will cancel and magnetic field would be mu naught Ni, where this N is what? This N is a number of turns per unit length, right? And your N is the total number of turns. And then this, yeah, so this would be the magnetic field of a solid. And we have calculated this magnetic field using the Ampere's law. So is it clear to you? Is this part? This is very important. Is this clear? Yes, is this clear,
Yes, sir.
Aslan? Yeah, so you have four regions. In one region, the magnetic field is perpendicular, so that is cos 90, that is 0. In this region, you don't have any magnetic field, so that is 0. In this region, again, this magnetic field is perpendicular, so this is 0. And in this part, this is the direction dA, which is same as the magnetic field. So the angle is zero. So that is how you get this, right? Please note it down, and then we'll talk about the other things. Quickly note it down, and if you have any confusion, tell me. Yeah, please note it down. Yeah, whenever you want me to scroll down the screen, please tell me. Yes, whenever you have noted it down.
Yes, sir, done.
Yeah. Okay. So remember, whenever we calculate the magnetic field of a solenoid, so that is always this is not mu naught Ni, not the number of turns, but this is mu naught Ni, number density, right? So you would be given a certain of the solenoid, you will be given, let's say that the total number of turns are 50, right? So let us do one question and this would be clear, right? Let's say that, yeah, so calculate the magnetic field of yeah, so calculate the magnetic field of a solenoid of length, let's say 20 centimeters, and having 500 turns, right? Where current is 3 amperes, right? So this is the question. So the current is given 3 amperes, and then you are given the length of the solenoid. So that is how much? 20 centimeter, which is 20 by 100 meters. So this is 0.2 meters. And then you are also given the number of turns. That is 500. So first you have to calculate this thing, number density. So this would be how much? How much would be the number density? How much would be the number density, epsilon? So number density is n by l. This is how much? This is 500 divided by 0 0.2. So this will cancel out.
Sir,
This is, yeah,
nothing, sir.
yes, yes, yeah, do you want to say something? Yes, please. If you have any doubt
No,
or meter. Yeah. So this would be the number density to 2500 turns per meter, and then we can calculate the magnetic field. So this magnetic field would be mu naught Ni. This is mu naught. What is the value of mu naught? What is the value of mu naught?
you notice.
Yeah,
Uh,
mu naught by 4 pi, that is 10 to the power minus 7, right? So mu
mm,
naught is 4 pi into 10 to the power minus 7. So mu naught is 4 pi into 10 to the power minus 7. N is 2500. And then you have this I, which is 3 amperes. And this would be Tesla. So this would be how much? So this is 25 forward, so 100. And then this 100 again, and then 3. And then pi and 10 to the power minus. So this is 10 to the power 4, right? 3 into 10 to the power 4 into pi and into 10 to the power minus 7. So this would be how much? This is 3 pi and 10 to the power minus 3 and 10, right? So this would be the magnitude. Okay, clear. And yeah, they generally ask this question in the exam. Magnetic field of solid. That is very important. Clear? Is it clear?
yes, sir.
Why are you appearing to be so quiet? What happened?
Yes,
Yeah,
sir.
please. Yeah. So, are you tired? Are you feeling
No,
tired?
sir, I can barely hear you. That's the problem, sir. My grandmother is
So,
playing
what?
something in the background. I can't hear you at all. So
Oh,
I am
okay.
losing focus and interest, sir.
Oh, yeah, yeah, yeah. So, I have increased the volume to the max.
No, sir.
Okay, so
Even if it's increased, I can still barely hear you.
okay, so please, yeah, then please note it down, and I will just start another topic and then we'll stop. Right? Please note it down. Quickly note it down. That's enough.
Yes, sir, done.
Okay, so the next topic is magnetic force. Right. The next topic is magnetic force. Magnetic force. And Lawrence. Okay, so first